This is the final stage of CHUMP and consists of 6 new chips: the control ROM, address accumulator, MUX, NOT, and RAM. Here's how it works. This is a block diagram of CHUMP, the cheap, homebrew, understandable, minimal processor. This 4-bit computer consists of 8 components: a program ROM, where the program is uploaded, control ROM, where the control code is uploaded, the multiplexer, the arithmetic logic unit, accumulator, address, program counter, and RAM. Each CHUMP program is in the form of a byte, an 8-bit value with the higher nibble defining the opcode and the lower nibble defining the operand as either a literal constant or the address of a memory location. The LSB of the opcode determines the constant or address, as 0 is a constant and 1 is the RAM address. The CHUMP program is capable of making 14 instructions as shown in this table, 2 for each of its primary functions: load, add, subtract, read, store to, which stores a value in the RAM address, go to, which skips to a line instruction, and if 0, which checks if the accumulator value is 0, and if so, skips to a specific instruction through the program counter. Back to the diagram, the PC provides the heartbeat for the project, and upon each rising clock pulse, advances to the next instruction. Next, the control ROM contains all the control codes, as shown here, which are necessary to decode the instructions it receives from the program ROM to the rest of CHUMP. This ROM has 5 control points: the multiplexer, which chooses the constant or memory value, ALU, which selects one of the arithmetic operations, accumulator, which will load or ignore the ALU's outputs, the RAM, which will either read or write, and the program counter, which will either load or increment. As the ALU has to perform multiple operations, it necessitates 6 control bits, 4 for S0 to S3 and 2 for mode and CN. There are a total of 10 control bits marked by the C flags in the diagram. Additionally, there is the Z flag, which is wired to the A equals B pin of the ALU. It is only high when all of its outputs are high, and it is paired with a control bit in the load pin of the PC. Values are loaded into the PC when either the C or Z flags are high. When neither of the C or Z inputs are high to the load, the PC increments by 1. These 2 flags are necessary for branching of addresses in CHUMP. Next, the multiplexer, dependent on the control signal, will either select the constant or memory operand. Next, the ALU acts as the brain for CHUMP, doing the arithmetic and logic operations. It's capable of 32 operations, but in this project only 5 are used: B, A plus B, A minus B, logical 1, and not A. The ALU takes in the opcode to select what operation to use. Loading and reading values requires the B operation, while addition and subtraction ones require the A plus B or A minus B operation. The go to and if 0 ones need a logical 1 operator. Once the ALU executes an operation, the output of the program is stored in the 74LS377 accumulator, which holds values due to its 8 edge-triggered D flip-flops. The accumulator's outputs are the most crucial in this project as they display the output of the program. Finally, the RAM is necessary for either writing or reading data. When a memory operation is executed, it must first enter the 74LS174 address chip, which also consists of D flip-flops to hold data. This chip dictates what address will be written or read to in RAM. And the RAM is a 64-bit and holds the memory values for CHUMP. Additionally, each triangle that appears on this diagram represents the clock pulse from the PC. Unfortunately, I couldn't get this 4-bit computer to work, but I plan on fixing it very soon.